Alright, so in this video I'm going to be explaining another important article. In the previous paper, I talked about graph random features. Now we are talking about another paper with the title Quasi-Monte Carlo Graph Random Features, NeurIPS 2023. This paper in NeurIPS 2023. So we present a novel mechanism to improve the accuracy of the recently introduced class of graph random features. Our method introduces negative correlations between the length of the algorithm's random walk by imposing antithetic termination, a procedure to sample more diverse random walks, which may be of independent interest. It has a trivial drop-in implementation. We derive strong theoretical guarantees on the properties of the quasi-Monte Carlo GRFs, proving that they yield lower variance estimators of the two-regularized Laplacian kernel under mild conditions. So, randomized mapping phi construct low-dimensional features, and their dot product equals the kernel evaluation in expectation. This permits a low-rank decomposition of the kernel matrix. The problem of poor kernel scalability is exacerbated in the graph domain because even computing the kernel matrix is typically of at least cubic time complexity in the number of nodes. This is why it's a central question of this work. How can we implement a QMC mechanism for random walks on a graph? What do we mean by a diverse sample in this context? So in classical physics, diffusion through continuous media is described by this equation. And this is the discrete heat equation. This discrete heat equation has this solution and the symmetric positive semi-definite matrix. With this inspiration, we can define it like this. And remember, L is just the Laplacian, diagonal minus weight. So this is the Laplacian, and we create a kernel out of that. We define this symmetric positive semi-definite matrix out of that, which is referred to heat kernel or diffusion kernel. And the exponentiation of the generator, which by construction captures the local structure of G, leads to kernel matrix, which captures the graph's global structure. And now this graph random feature is very important. If you go through that, to construct phi of I by taking m random walks on the graph out of node I, we deposit a load at every node that depends on first the product of edge weights traversed by the subwalk, and then the marginal probability of the subwalk. Importantly, each walk terminates with probability p at every time step. So this is the x component of the ith random walk feature. Here omega 1 is particular random walk, the set of random walks between node I and x. And omega tilde here is the product of weights of edges traversed by the walk w. And p is the marginal probability that the walk contains a prefix suffix subwalk w omega 1. So we now present our novel termination mechanism. We have seen that IID implementation of GRF, each walker terminates independently with probability p at every time step. For a pair of IID walkers out of node I, this is implemented by independently sampling two termination random variables. Each walker terminates if its respective TRV is less than P. So we refer to a pair of walkers as antithetic if their TRVs are marginally distributed. On the left, you see the schematic of IID, GRF, and QGRF mechanisms. On the right, you see demonstration with 4 random walks on the karate graph. Since the marginal distributions over T sub I are unchanged, our estimator remains unbiased. But the coupling between TRVs lead to statistical correlation between the walkers' termination.